Let's make use of these antidifferentiation theorems involving trigonometric functions in solving for the antiderivatives of the given items. We have a separate video that discusses antidifferentiation techniques by using theorems 1.3 to 1.7. If you want to get reviewed by this video, just click the suggested video there at the upper right corner of your screen. For our first item here, clearly we are to use theorem 1.5 and theorem 1.4. That is, we are to use theorem 1.5 to separate the two given functions here. And so we have 3 times antiderivative of secant x tan x dx minus 5 times antiderivative of cosecant squared x dx. So again, if you want to have a discussion on how to make use of theorems 1.3 to 1.7, just watch first the suggested video there at the upper right corner of your screen. As for the antiderivative of secant x tan x dx, definitely we can use theorem 1.12, and the answer there would be secant x plus c. And multiplying that to that 3 there, that's why we have 3 secant x. As noted in that suggested video, we can actually just group all our c's here and just have the plus c there at the last part of our answer. Next would be negative 5 times antiderivative of cosecant squared x dx. And using theorem 1.11, its answer would be negative cotangent x plus c, and so we have negative 5 times negative cotangent x plus c. Simplifying this, we'll now have 3 secant x plus cotangent x plus c. If you want to be reviewed by operations on integers, just click the suggested video there at the upper right corner of your screen. From the given item, we can have the antiderivative of 4 cosecant x cotangent x dx plus the antiderivative of 2 secant squared x dx with the use of theorem 1.5. And using theorem 1.4, we can separate the constants there 4 and 2. That's why we have this. Now using the corresponding antiderivative theorems, that would be theorems 1.13 and 1.10, we now have this. Distributing the constants 4 and 2, we now have negative 4 cosecant x plus 4c1 plus 2 tangent x plus 2c2. Since 4c1 and 2c2 are constants, we can generally write plus c. But how about this? Notice that we don't have antiderivative for tangent squared x and cotangent squared x. This kind of problem calls for trigonometric identities. You'd know that you are to use trigonometric identities if these theorems will not lead you in getting the antiderivatives of the given item. We have here secant squared x minus 1 instead of tan squared x by manipulating algebraically this trigonometric identity tan squared x plus 1 equals secant squared x. For the benefit of others, we just transposed positive 1 to the right side of the equation. That's why we have tan squared x equals secant squared x minus 1. Similarly, for cotangent squared x, we can use this trigonometric identity and substitute cosecant squared x minus 1 for cotangent squared x. Using now theorems 1.5 and 1.6, we can now get the antiderivative of each of these functions. So for the antiderivative of secant squared x dx, we can use theorem 1.10 and have there tan x plus c. And as for the antiderivative of cosecant squared x, we can use theorem 1.11 and have there negative cotangent x plus c. For the benefit of others, the reason why we have positive 2 there is actually because of negative 1 minus 1 plus 4. And using theorem 1.3 to this, we now have positive 2x. And again, we have the plus c there to sum up all the c's that we had earlier. So yes, you'd know when to make use of these trigonometric identities if you'd see that these theorems right here would not give you the antiderivatives of the given items. Just like in this next item, notice that we don't have antiderivative for these trigonometric functions. I have discussed a technique in getting the antiderivative of division of functions. If you want to review that technique, just click the upper right corner of your screen for that suggested video. In that video, it was discussed that we just have to decompose this fraction. That is, we can separate these two fractions and have the antiderivative of 2 cotangent x divided by sine x minus 3 sine squared x over sine x dx. For the benefit of others, this is having like the sum of x and y all over c that is being separated as x over z plus y over z. Now having the concept of multiplying fractions, this is the same thing as 2 times 1 over sine x times cotangent x. If you want to be reviewed multiplying integers, just click the upper right corner of your screen for that suggested video. Using this trigonometric identity, 1 over sine x is the same thing as cosecant x. Clearly, we just have to copy cotangent x because we have antiderivative of cosecant x cotangent x dx, which is theorem 1.13. We can simplify sine squared x over sine x and just have sine x. For the benefit of others, this is the same thing as x squared over x, which is just equal to x. So yes, applying theorem 1.13 to this, we have negative cosecant x. And to answer the antiderivative of sine x, we just have to use theorem 1.8 to have their negative cos x. Distributing the constants 2 and negative 3, we now have negative 2 cosecant x plus 3 cosine x plus c.